All right, we're working on angle versus period. It's the pendulum lab that we did with that. And I have sped things up just a tad by drawing the lines. I've obviously got my numbers filled out in there. So I drew my L. I divided up the bottom line into 10 equal parts as best I could. Put a halfway mark, one at the end, halfway, and then 5 in between. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the numbers along that axis obviously need to be the X, the independent, 5, 10, 15, 20. So I'm going to put 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. So there we go. All those numbers transferred down here. Now, the question is, and I've already put marks halfway and 4 equal parts. I put one there. The process I do is the end, the middle, and then the middles of those. And so now the question is, do we go from 0 to 2? Because our numbers are basically 1.6 to 1.7. So let's see what will happen if we do 1 and 2, which you mean this would be 0.5 and this would be 1.5. Okay, everybody following along with that? See how I've got it? And that means all of our numbers are going to fall in this range right here. It's going to be pretty cramped. And what I'll probably do is do another video where instead of doing 0 through 2, maybe I focus in on this, squish this down. Since there's no information down here, we could squish it down and do that little squiggly line thing and essentially zoom in on so we can see better what's going on with the line. But anyways, for this version, I'm going to go with this way. 1.67 would be, if this is 1.5, then we need to put 6, 7, 1.6, 1.7, 1.8, 1.9. That's not too bad, huh? Look at that. Pretty even. And these are most important lines because, like we said, all the information is between 1.6 and 1.7 or 8. All right, so this is 1.6. This is 1.7. 1.8. Capiche? 5, 6, 7, 8. You see that? Okay, now should probably create some guidelines, some very light lines to guide us, especially on the 1.6, 1.7, and 1.8. Okay. Those are very light. Now, let's see, 1.67, if that was, see, we need 1.67, so I got to put a halfway mark between 1.6 and 1.7, because that'd be 1.65, right? If you know how your decimals work. That's 1.65. 1.65 is right in there. But we have 1.67, almost 1.68. So we're even higher, 1.68, like right about there. Now, vertically, it comes up from the 5 and then comes across. So we're right about right there. You guys see how that works? If halfway is 1.65, we're a little higher than halfway. Pretty close. Now 1.681 for the second one, the one that goes with 10. 1.6816. So We've got to be just a tiny bit higher than that. Hope that's obvious. I made it just a tiny bit higher. 1.685 is the next one. So just the fact that this is so squished, it's so hard to, even draw it, is evidence or reason for doing what I said I'll probably do in the next video, which is expand this zone here so that it's taking up the whole sheet. That way it's easier to, differentiate the points. So 1.685, I guess that'd just be a touch higher than that other one. But it feels so much like just guessing here. 1.69, so that'd be, gotta make our guide. 1.69 would be just very close to that line. So we're getting just a tiny bit higher each time. And then the next one's even closer, like super close, 1.6986. That would easily round up. Just super close. And 30. Goes, now we've made it past 1.7. Everybody see how that line is 1.7. So now we've been creeping closer and closer to that line, and now we're just a tiny bit higher than that. So put the dot like so. That even looks like I'm on the line practically. It's really difficult to do. All right. Next one is 1.71. 1.71 would be a touch higher. And down here when I did my guide, I felt like that 40 tick mark was a little too far to the right, so I scooted it back just to try to fix that problem. So 40 goes up to 1.73, so that's a bit higher. And see how 1.73, because if it was 1.75, it'd be right in the middle, right there. But it's a little less. Next one is 1.745. I'll go ahead and do the guideline for 50 as well. 1.7, where's that? 4 would be very close to the middle. You guys see that? It's 1.74, so it's almost 1.75. That's why I'm almost halfway. Okay, then 50, it's 1.76, so we've gone past halfway. Everybody see that now? I'm a little higher than the halfway point. All right, so now we make a best fit line. Not too hard. And the slope of that line is pretty flat, but it definitely is increasing just slightly. So as you increase the angle, the period increases slightly. So the angle doesn't have that much of an effect. That's what that means. If a line, the flatter the line is, the less of an effect. Eventually, if you had a totally flat line, that would tell you that the angle has no effect on the period, because the period would just stay the same all the time. All right? So in another video, I will expand this and just show you how it's easier to draw all these points if we zoom in on that zone right there. But the flatness is much easier to notice when the scale is appropriate like this. So Yeah, I'm not sure if I'll make another video where I expand on it, but it is definitely a skill to know how to expand, how to zoom in on that. All right, that's it for this one. Thanks for following along. Okay, to finish off this lab, angle versus period, we just did the graph, and I just remembered that we haven't written our conclusion or sources of error yet. So for the conclusion, it's pretty much state whether or not the data supports our hypothesis, just like it says here, then restate the hypothesis in a simple sentence. So, you know, what I said in my hypothesis was, if I release the pendulum from a greater angle, so a greater angle, the period, which is the time it takes to complete a full cycle, will increase. So if you've heard of hypothesi, if that's a word, plural for hypothesis, hypotheses, that's it. If you've heard of hypotheses, you want to make a prediction. And I definitely did. I stuck my neck out. You know, I allowed myself to be right or wrong. I said, if I release the pendulum from a greater angle, then the period will increase. What we did see was, as we increased the angle moving to the right, it definitely, you know, got taller. The line slopes up. So I want to say the data supports my hypothesis. And I think it's fair to say, you know, just communicating with people here, the data supports my hypothesis, but only barely, right? Because I'm saying, you know, I thought the period would increase as I increased the angle, and I was right, but only barely, because it's practically flat. So you say, referring back to this, teaching you how to, you know, read what I wrote. State whether the data supports your hypothesis. I did that. Then restate the hypothesis. So next we need to restate the hypothesis, and listen to the way it flows. The data supports my hypothesis, but only barely. As I increased the angle, I'm gonna have to turn sideways here. The angle, the period increased a tiny bit each time. And isn't that true? That's exactly what happened. So sources of error, we want to say, and the guidance here says this is where you explain all the little ways unintended variables get into your experiment. Now, we did this experiment not in real life, but on the computer. So the computer, it's like the realm is too perfect. So we've almost got to pretend that we did it in real life. You know, if I suspended it from my desk here with a hook or something, what factors, what unintended variables would get in? Let's say, for one, starting and stopping the timer had been a real challenge. So starting and stopping the timer will always be a source of unwanted variables. How about in real life, holding the pendulum at exactly 5 degrees, exactly 10 degrees, right? The more exact that has to be, it's impossible to get it exact. We can get very close, but so let's see, releasing the pendulum from the exact angle. Yeah, that is definitely a source of error. And what I'm looking for in sources of error is like 2 or 3 different 2 or 3 different statements about potential variables. What would be another one? I guess you could say maybe the wobble. Like in real life, you let go of a pendulum, it sometimes wobbles because of the way you let go of it. Any wobble, that's a funny word, wobble in the pendulum could affect and yeah, so if there's any wobble in one trial that's not in another in exactly the same manner, definitely. And then friction, I would say friction, each time you release the pendulum, whatever angle you're releasing it from, there's a little bit of friction on the string and the hook. And you could imagine that, it's different each time. Like there's more friction on the greater angles than on the lesser ones. So that's plenty. There's how you finish the write-up. And don't forget to put your name, Fred, and I'll put myself in the 0th period because I'm the teacher. All right. Thanks for watching.